Good evening, it's Chris Potter. It's May 18th, 2017. Sharing an article from NASA's Jet Propulsion Laboratory, dated November 10th, 2016, but I feel it is very relevant. Pardon me, the name of the article, NASA Space Telescopes Pinpoint Elusive Brown Dwarf. The illustration below depicts a newly discovered brown dwarf, an object that weighs in somewhere between our solar system's most massive planet, Jupiter, and the least massive known star. Credit NASA, JPL, Caltech. I'll put the link below. This should be about 10 minutes. I hope you can bear with me. Thank you for subscribing. Thank you for watching. I'm going to continue to put out these articles that I'm finding online. I find that they're extremely relevant to the research that we're doing. In a first of its kind, collaboration, NASA's Spitzer and Swift space telescopes joined forces to observe a micro-lensing event when a distant star brightens due to the gravitational field of at least one foreground cosmic object. This technique is useful for finding low-mass bodies orbiting stars such as planets. In this case, the observations revealed a brown dwarf. Now look, folks, I don't trust a damn thing that NASA says, but we'll go ahead and put out the information anyway, because, again, I find it relevant. Brown dwarfs are thought to be the missing link between planets and stars. I totally agree. With masses up to 80 times that of Jupiter. But their centers are not hot or dense enough to generate energy through nuclear fusion, the way stars do. Curiously, scientists have found that for stars roughly the mass of our sun, less than 1% have a brown dwarf orbiting within 3 AU. 1 AU is the distance between the Earth and the sun. This phenomenon is called the brown dwarf desert. What? Interesting. Okay. The newly discovered brown dwarf which orbits a host star may inhabit this desert. Yeah, brown dwarf desert action. Spitzer and Swift observed the micro-lensing event after being tipped off by a ground-based micro-lensing surveys, including the optical gravitational lensing experiment, OGLE. Another newbie for me. The discovery of this brown dwarf with the unwieldy name OGLE-2015-BLDG-1319 marks the first time that two space telescopes have collaborated to observe a microlensing event. We want to understand how brown dwarfs form around stars and why there is a gap and where they are found relative to their host stars. I find this a very interesting article, said Yossi Schwarzwald, a NASA postdoctoral fellow based at NASA's Jet Propulsion Laboratory, Pasadena, California, and lead author of a study published in the Astrophysical Journal. Looks like I need to be checking that journal out. It's possible that the desert is not as dry as we think. Ha! Ha! What is microlensing? In a microlensing event, a background source star serves as a flashlight for the observer. When a massive object passes in front of the background star, along the line of sight, the background star brightens because the foreground object deflects and focuses the light from the background source star. Depending on the mass and alignment of the intervening object, the background star can briefly appear thousands of times brighter. Very interesting. This is all very interesting. One way to understand, it just reaffirms all of the work we've done with the physicist. Wow. Wow. Any claims that she's a fake physicist is ludicrous. One way to understand better the properties of the lensing system. Interesting that they say lensing system, by the way, for other reasons, is to observe the micro-lensing event, pardon me, from more than one vantage point. By having multiple telescopes record the brightening of the background star, scientists can take advantage of parallax. The apparent difference in position of an object is seen from 2 points in space. When you hold your thumb in front of your nose and close to your left eye, then open it and close your right eye, your thumb seems to move in space. But it actually stays put with 2 eyes open, right? In the context of microlensing, observing the same event from 2 or more widely separated locations will result in different magnification patterns. Anytime you have an opportunity for multiple observing locations, such as Earth and 1, or in this case 2, space telescopes, it's like having multiple eyes to see how far away something is, pardon me. Schwarzwald said, from models for how microlensing works, we can use this to calculate the relationship between the mass of the object and its distance. And I like this little article, even though it is from Never a Straight Answer. Pukes. The new study. Pardon me. Spitzer observed the binary system containing the brown dwarf in July of 2015 during the last 2 weeks of the Space Telescope's microlensing campaign for that year. While Spitzer is over 1 AU away from Earth and an Earth trailing orbit around the Sun, Swift is in a low Earth orbit encircling our planet. We saw the same thing from the physicist in my last presentation. Well, her last presentation. Where we're talking about Core A, the Core A and Core 2B, Core 2A and Core 2B satellites. Like the same, one's in front of the Earth and the other's behind it. The dude in front is going a little bit faster, the dude in back is going a little bit slower. Again, this absolutely parallels the work that the physicist has put out in her articles. Wow. I think it's significant. But Swift is not far enough away from ground-based telescopes to get a significantly different view of this particular event, so no parallax was measured between the two. This gives scientists insights into the limits of those telescopes' capabilities for certain types of objects and distances. Our simulation suggests that Swift could measure this parallax for nearby less massive objects, including free-floating planets, which do not orbit stars, Schwarzwald said. That's interesting. By combining data from these space-based and ground-based telescopes, researchers determined that the newly discovered brown dwarf is between 30 and 65 Jupiter masses. Again, we're seeing some serious common themes between the articles that I've read over the last few days and all of the presentations that the physicist has done. It's like a second witness, a third witness as to the work that we're doing. Come on. Hello? Okay, so 30 to 65 Jupiter masses. That's massive! They also found that the brown dwarf orbits a K-dwarf. What? A type of star that tends to have about half the mass of the Sun. Researchers found 2 possible distances between the brown dwarf and its host star based on available data, 0.25 AU and 45 AU. The 0.25 AU distance would put this system in the brown dwarf desert. In one of the presentations from the physicist, she put the brown dwarf affecting the sun as 0.25 or 0.35 AU away from the sun. I think it's 0.25. Just saying. Interesting correlation there, boo. Brown dwarf desert. Interesting. In the future, we hope to have more observations of microlensing events from multiple viewing perspectives, allowing us to further or probe further the characteristics of brown dwarfs and planetary systems, said Jeffrey Bryden, JPL scientist and co-author of the study. We'll just go ahead and wrap this up with some of the technicalities of the article. JPL manages the Spitzer Space Telescope mission for NASA's Science Mission Directorate, Washington. Science operations are conducted at the Spitz Science Center at Caltech in Pasadena, California. Spacecraft operations are based at Lockheed Martin Space Systems Company, Littleton, Colorado. Actually, I didn't know any of this. The data are archived in the Infrared Science Archive, housed at the Infrared Processing and Analysis Center at Caltech. NASA's SWIFT satellite was launched in November 2004. Oh. And it's managed by NASA's Goddard Space Flight Center in Greenbelt, Maryland. Very interesting article. I will put the link below. Thanks for watching and subscribing. Gosh, this is just really interesting, isn't it? Take care. Have a good day. Bye.